Hi, I'm Jacob Boyer,
And I'm Yara Williams.
and we're presenting symmetric structures of viruses. Symmetric structures are beautiful and powerful mathematical tools that are prevalent in many fields, including virology.
In the field of virology, some viral capsid shells follow an icosahedral arrangement which sheds light on virus structure. Through this project, we explore symmetric structures of viral capsids in order to classify viruses and aid in the development of more efficacious drugs and treatments. For background, as discovered by James Watson and Francis Crick, the viral genome encoded for instructions was repetitive for the formation of the capsid protein, indicating symmetry was present in the virus. Capsid protein shells self-assemble, inducing folding of their proteins to virus-like particles to produce the virus structure. Furthermore, it was found that viruses compact their genome using icosahedral and geodesic symmetry.
Expanding upon the icosahedral model, Casper and Klug generalized a model for triangulating the icosahedron known as the Casper-Klug model of quasi-equivalence, which describes all possible icosahedral structures and gives the definition of the triangulation number, T equals b squared plus bc plus c squared, where b represents the steps from the edge of a pentamer and, upon turning 60 degrees counterclockwise, taking c steps to reach the next pentamer. This particular shape gives insight into more than just virus structure. Triangulating the icosahedron yields the T number, the most important piece of the icosahedral puzzle. As we triangulate an icosahedron into more triangular facets, a geodesic formation arises as demonstrated in figure 2. The T number determines the number of capsid proteins within a shell. For all viruses that can be modeled by an icosahedron, there will be 60 T capsid proteins within that virus, in addition to 12 pentamers and T minus 1 times 10 hexamers.
The relation of mathematical symmetry and virology are connected through viral capsid structure. The capsid encodes the biological organization and function of the virus. It serves to protect the virus nucleic acid instructional code. With that being said, the RNA or DNA determines the size and structure of the capsid. The proteins in a capsid are composed of amino acid by chemical bonds. Knowing how those chemical bonds react it is important in knowing how the capsid would give RNA or DNA in a virus access to a host cell and persist in the environment. To combat the persistence of viruses, vaccines are used. The process includes identification of the atomic structure or antigen antibody complex in relation to the spike proteins. Once established, reverse molecular engineering remodels epitopes and integrates the strain for a vaccine.
We have started to implement an algorithm using Lindenmayer systems or L systems, a type of grammar for writing fractal structures. The folding structure of capsid proteins has been observed to be partially fractal. Proteins fold at certain angles and can be thought of as one-dimensional curve through 3D space. We can represent the shape of these proteins as a string of characters representing the angles between each amino acid in 3D. We are working toward finding an L system to represent this string as a series of repeatedly applied substitution rules. By classifying the possible structures that a virus can take, we can help develop methods that inhibit these structural changes and prevent viral infection.
We wish to continue this project by studying systematic structures as they relate to chemical composition and conformational changes of viruses. Developing a better understanding of the virus can help understand its nature, evolution, and adaptation. Thank you for your time and attention.